Hello, everybody. I'm Victor Cabrera. I'm from Ecuador. I'm going to present you a research that we are ongoing with some students and some teachers from Ecuador, Universidad Politécnica Salesiana. That's the university where we are working. So what we are going to show to you is the research about determination of fluid velocity in microfluidics devices with variable channel widths by rectangular patterns using SLA, additive manufacturing. First of all, we want to start because our research start to be developed because we analyzed that the importance of micro devices and additive manufacturing during the last years has been a really important technique and really important process that many industries and many researchers are taking on. So during the last 20 years, we can see that the trend of 3D printing, microfluidic, and additive manufacturing published articles has increased. So in that way, we start to analyze what would be an application to this kind of technologies. So we're going to start explaining what is the normal manufacture process that we have now. The most common process is PDMS. That is the traditional research technique in order to make micro devices and chips. So what we are looking to do is like get or use a different manufacturing process. One of it is thermoplastic polymers, so that's what we are using. In that sense, we are trying to apply this kind of new technologies in order to get different alternatives to the traditional process. So what the traditional process do is you have a master, and this master you do by the soft lithography, and you use this master in order to get a PDMS mask, and this PDMS mask is using for the micro device. So what are the difficulties in this traditional process? It's time consuming because manufacture the master is take a couple of weeks, so that make that you cannot go as fast as you want in the research. Limited stamp lifespan. So when you have the stamp already, you can use just for a limit number of times. So that means that you cannot have this kind of stamp as long as you want. Um, Limited substrate size. So according to the process, you just could build a small size devices. In that sense, you cannot expand your technology to get a bigger devices. And finally, the variability is because you have this kind of limited stamp lifespan. So that means that you are going to destroy a little bit the master, and that means that you are going to lose some quality in your device. So and finally, if you want to take this process to mass production, is going to be difficult because this technique cannot allow to do that. So what we are offering is like printing devices or small devices, but 3D printing, or the right name of this technology is additive manufacturing. And the most used technologies are FDM and PolyJet, but we are using SLA technology in order to improve a new technique, and this technique can allow us to get a good results. So how SLA works is like you have a tank when you have liquid resin, and then you start to solidify the resin by a laser. So you are going to add all the layers on the device, and then you get this kind of parts. You first design, and then you print the part, and then you get what you see at the right. So the first part of the research was refine the printing process, because you cannot get as small channels as we want. So we normally the process has a design, print, clean by isopropyl alcohol, and cure by UV rays. So what we add is this step that is air clean. What we help us this air clean is to take it out all the liquid resin, and then allow us to get a clear channels to the process. So what we do in this research, so we are going to know, or we want to know, what is the behavior of the fluid along a channel with rectangular variations. So normally we understand when you have a bigger channel, normally the speed of the fluid is going to be down. So that is the hypothesis that we have. But we are going to show us what was our end result. So this is the channels that we use. The variation was from 400 each one to 600, 800, and 1000. So you can see it's like a straight channel, and then we have a variation inside the channel. Though this we are working with microns. So how you can see at the screen. So what we use, the characteristic of our research is that we don't use a pump or external sources. So what we use is a capillarity, that is a property of the fluid with a smaller channel. So what we do is like allow us to the fluid to go through by itself. So after we start to the methodology, the first thing that we do is like put a drop over the tank that you can see at the right over here. So and then we start by capillarity, make the fluid pass through the channel, like you can see at the screen. So with this tracker, that is a free software, so we can take off the speeds of the liquid, and then we compare and analyze the data. So what we do first is like split the device by sections, and then we analyze what is the speed in each section and compare with the section before or with section after. So the first thing that we can say that is important is that this histogram is the number of velocities that we have in each value. So what we can say is that the device with smaller differences has a bigger number of speeds close to zero. So that means that this device is going to make the fluid go slower compared to the other ones. So that is a really interesting point because we cannot expect that thing, and we start to know how the fluid behave during this channel. So after that, we compare with each average velocity of each section. And we can see that at the beginning, the straight part that is a smaller channel, 400 microns. So it's going to be slower compared to the second one. So that happens in all of the devices. And after that, we can have in the section B, we have this kind of variation of the channel, and then increase in 200 to 600, and then we can see that the velocity increase. So that's a really interesting point. And then we go to the straight part and then go down. So we can see that in the wider channel, so the velocity is higher compared to the smaller channel. So that is a really interesting point. Another thing is that we normally the capillarity is a property that can allow to the fluid to keep the velocity, but we can see that the variation of the channels make that you are going to reduce the speed along the channel. So we can see that at the G section we have a lower velocity compared to the other one. But in the device that we have less variation, so we can see that the speed keep an average along the section. So in bigger differences, we have this kind of velocity reduction considerably compared to the other one. So at the end, what we do is like have an average of the speeds along the channels. And we can see that in the device that we have differences from 400 to 600. We have slow, the smaller, standard deviation. So that means that we have more stability at the velocity. And when we have a bigger differentiation from 400 to 1000 and 1200, so we can see that we have a bigger standard deviation. So that means that the devices will have a bigger difference of the channels is unpredictable. So we cannot control the velocity as good as we want. But we know that the velocity is going to increase or decrease, mostly compared to the smaller ones. So at the end, we have this conclusion. So the technology that we use, SLA technology, is appropriate in order to get the devices that we can use with microchannels. So using the technique that we already refined. So at the end, we have this kind of differences results between 600 with the channel variation between 600 to 1200 microns. So we cannot compare each other because the behave from the smaller channel compared to the bigger channels are really different. But we can say that when we make the channel bigger, the velocity increase. So that's a good point, a good characteristic that we want to apply in future research. At the end, what we can say is that the smaller channel size, we can see that we have lower velocities, and that means that when we increase the size of the channel, we are going to increase the velocity. That is a characteristic that is important to us in order to develop future device. Thank you so much. I hope that my presentation